Year 13, Year 1, Further Maths, Sequences and Series, Lesson 3, Proof by Induction. So before we introduce this new method of proof, we're going to go back and revisit some of the examples of different types of proof that you have come across before. And we're going to start with proof by deduction, and we're going to use this to prove Pythagoras' theorem. So have a look at the diagram on the left-hand side here. We're going to write down a result that will give us the area of the blue square. So the area of the blue square could very simply be described as c squared if we just take the area directly like that. But we could also say that the area of the blue square is equal to the area of the large square subtract the area of the 4 right-angled triangles. So let's work this out. Now, what's the area of the large square? The area of the large square is a plus b multiplied by a plus b. So the area of the large square is a plus b all squared. Now, what about the area of these triangles? So we need to subtract 4 multiplied by a half multiplied by ab. So if we simplify this, this gives us a squared plus 2ab plus b squared minus 2ab, or a squared plus b squared. Now, both results give us the area of the blue square, so from here we can conclude that a squared plus b squared equals c squared. And that is a very simple proof using algebraic deduction, where you take a series of logical steps and you simply build on them, where every step you make relates back to the information that you've been given, and you're only using facts, statements that are true, to go from step to step until you deduce the result you wish to prove. Now, you may also have come across the concept of proof by contradiction, and we're going to take a very typical example here where we prove that root 2 is an irrational number. Now, the whole basis of proof by contradiction is that you start by assuming the converse. So we're going to assume that root 2 is rational, which of course we know it isn't, but that's the whole basis of this proof. So we assume the opposite of what we are trying to prove. Now, from here, we can then deduce if root 2 is rational, then it must be feasible that we can write root 2 in the form p over q, where p and q are integers, and this fraction has been simplified to its simplest form, so p and q have no common factors other than 1. There's a nice mathematical term for two integers which have no common factors other than 1. We can call them co-prime. Now, what can I deduce from this statement that I've written down? Well, I'm going to square both sides, which I can do because they are equal to each other. So this then gives me 2 is equal to p squared over q squared. And from here, I can rearrange this so that it tells me that p squared is equal to 2q squared. Now, this tells me that p squared must be an even number, because it's 2 lots of something. It's a multiple of 2. Now, if p squared is an even square, this tells me that p is even, which tells me that I could write p in the form 2m, because it's an even number. Now, if p can be written as 2m, then I can say that 2m squared is equal to 2q squared, or 4m squared equals 2q squared, which tells me that q squared must equal 2m squared, which tells me that q squared is even, which tells me that q is even, which means I can write q in the form 2n, because it's an even number. Now, if we then go back to this statement up here, this tells me that root 2, which is equal to p over q, can be written as 2m over 2n, or m over n. Now we have a contradiction here, and a problem, because we said that p and q were integers with no common factors other than 1, and we've shown that's not the case. They're both even, so they have a common factor of 2, and here is our contradiction. Now, the fact that we have a contradiction means that our original assumption at the very start, right back over here, must be false. So our whole argument here has been built on a false statement. And that's how proof by contradiction works. You assume the opposite of what you're trying to prove, and then demonstrate that this results in a massive contradiction, which means your original statement must be false, and there you have your proof. So we're now going to, in this lesson, introduce something different, a different format of proof, which is called proof by induction. Now, I like to introduce this by using a tower of bricks analogy. So I want you to imagine a tower of bricks. Now, to start off with, you don't know the colour of these bricks, but what you can do is you can prove that the very first brick is red. Now, you're then going to make the assumption that another brick in the pile, let's call it brick K, and let's pick this one at random. It's not meant to be the fourth brick, it's just a brick in the tower of bricks. Let's assume that brick K is also red. Now, if you can then prove that if brick K is red, then the brick above it, brick K plus 1, also has to be red, then what have you done? Because we know the first brick is red. You have then said that if we assume that one brick is red, brick K, we can then prove that the brick after that is red. Because the first brick is red, what can you then conclude? Well, you can conclude that all the bricks have got to be red, and that is the process of induction. And it's this key principle here, by proving that if you know one brick is red, i.e. this brick here, you then know the brick after it is also red. Because you already proved that the first brick is red, using what you've done here then tells you that the second brick has got to be red, and the third brick, and the brick after that, and all the bricks after that. And that is the process of induction. It's like toppling over a series of dominoes. So, how does this apply in a more mathematical sense? Let's have a look. We are going to prove by induction that the sum of the series 3 plus 10 plus 17 plus ... up to the nth term is equal to a half n 7n minus 1. Now, you may have spotted that this is an arithmetic progression. So all we're doing is finding the sum of n terms, which of course is given by the formula which you proved when you looked at sequences and series in your Year 2 A-level content, a half n 2a plus n minus 1d. So 2a is 2 multiplied by the first term, which gives you 6. N minus 1 multiplied by d. D is the common difference of 7, so that's 7 bracket n minus 1. So that simplifies to give you a half n 7n minus 1, which of course is that result there. So what we're doing is we're actually going to find this result. We're going to prove that this result is true, but we're going to prove it by induction. So think about the steps. We're going to start by demonstrating that the result is true for n equals 1. Now, how do I know to start with n equals 1? Well, in the question it says we need to prove this is true for all positive integers n, and the first positive integer is 1. So if n equals 1, well, that means we're thinking about the first term of the series, so the left-hand side is just equal to 3. Now, the right-hand side, I'll take this result here, the one that we're trying to prove, and we will substitute into it and see if we get 3. So that is a half multiplied by 1 multiplied by 7 times 1, which is 7, take away 1, which of course gives us an answer of 3. So the result is true for n equals 1. And by the result, I mean this formula here for the sum to n terms. It's true if you only have one term in your series. So we now assume that the result is true for some integer n equals k. Now, what do I mean by this? I mean that we're adding together 3, 10, 17, however many terms, up till the kth term, which would be 7k minus 4, and we're assuming that the formula that gives us the total of the terms is true for n equals k, so we're assuming that this would then be equal to a half k, 7k minus 1. So always write out your assumption. So we're assuming this result here is true. Now, based on this assumption, which we're allowed to take as true, we're now going to consider the next case where n equals k plus 1. So look at the left-hand side. That means we are taking 3 plus 10 plus 17 plus all the way up to term k, which is this, and we're adding on term k plus 1. So here, I replace n with k plus 1 on the left-hand side. So I want 7 k plus 1 minus 4. And that is the k plus 1th term. Now, what do I have here? Well, let's think about this carefully. These terms added together, well, that's the sum of the first k terms. And over here, we said that we were going to assume that the sum of the first k terms was equal to a half k, 7k minus 1. So that's the sum of the first k terms. And we're adding to that the k plus 1th term, which is 7k plus 1 minus 4. So what are we going to do now? Well, we're going to simplify what we've got and see what we can conclude about it. And we'll be continuing this on the next slide. So I'm going to simplify what I've got here. So I've got 7 over 2 k squared minus a half k plus 7k, and then 7 minus 4 gives me my plus 3. So here's what I'm going to do. I'm going to take a factor of a half out of this, which gives me 7k squared minus k plus 14k plus 6, a half 7k squared plus 13k plus 6, and this can be factorised. So we get a half k plus 1 multiplied by 7k plus 6. Now, what's the significance of this? Well, I'm just going to do a little bit of rewriting here. I'm going to take this part here and I'm going to rewrite this as 7 brackets k plus 1 minus 1. Now, of course, you can see that the two parts I've underlined in yellow are identical. I've just rewritten the second part slightly differently. Now, what's the significance of this? Well, we need to go back and remind ourselves what we were trying to actually prove at the start of this. We were trying to prove that our sequence, which was 3 plus 10 plus 17 plus all of the terms up to and including the nth term of 7n minus 4, is given by this formula here, a half n 7n minus 1. So that's the sum of however many terms. Now, look at the result we have got. Can you see, in place of n, we have k plus 1, here and here. So what we have done is we have added together the total of the first k plus 1 terms, and we have proven that it takes the same format as the formula we are trying to prove. So this is the result we are trying to prove with n replaced by k plus 1. So this means that if the result can be assumed to be true for n equals k, it is also true for n equals k plus 1. What we're saying is if we can use that formula for the sum of n terms to add together k terms, then that formula is also correct if you add together k plus 1 terms. Now, because we showed that the formula was correct when you had one term, well then by induction this must be true for when you add together 2 terms, and then by induction it must be correct for when you add together 3 terms. So it must be true for however many terms you add together. So let's very briefly talk through what we did here. We were trying to prove that the sum of n terms of this series here is given by this formula here. We proved that the formula on the right-hand side, this formula with all the arrows pointing to it, was correct for when you have n equals 1, for when there's only one term in the series, that term being 3. We then assumed that this formula was true for when you have k terms in the series. And we proved on the basis of that assumption, if it's true for when you add together k terms together, it must be true if you add together k plus 1 terms. Now, that means by induction, if the result is true for one number, it's then true for the number after that. And because we proved that the result was true for n equals 1, by induction, it must be true for n equals 2, and then for n equals 3, and so on, which means that the result, i.e. this formula here for the sum of n terms, must be true for all values of n. Now, you may have found that quite a complex process. Don't worry, we're going to look at a few more examples together. So, example 2. We are going to prove, using induction, that the sum of n terms of this series here is given by this result. Now, you've come across this result before. This result here is referring to the sum of the square numbers, 1 squared plus 2 squared plus 3 squared, all the way up to n squared. And we're being asked to prove that this is equal to n over 6, n plus 1, 2n plus 1. Now, we know this because this is one of the standard summation series results that we've looked at and we've used in a previous lesson. Now, if you recall, in that lesson, we said that we would prove the results for the sum of the squares and the sum of the cubes a little bit later on, and for the moment, previously, we just made use of those results without actually having to prove them. But we're now going to use proof by induction to prove this result. So, first step, prove that the result is true for your starting value of n, which of course is 1. So how do I do that? Well, look at the left-hand side. If n equals 1, that means we're adding together one term, which means the left-hand side is 1 squared, or 1. Now, the right-hand side, that means we want to prove that this result will give us the correct total if we add together the first square number by itself. So we simply substitute n into the right-hand side. And of course, what do we get? We get a value of 1. So this means the result is true for n equals 1. And what do we mean by the result? That means that the formula here for the sum of n square numbers, n consecutive square numbers, is true if you only have the first square number. So now what are we going to do? We're going to assume the result is true for some n equals k, where k is some integer. Now that means that we're assuming that 1 squared plus 2 squared plus 3 squared plus 4 squared plus however many square numbers we need to get to k squared is equal to k over 6, k plus 1, 2k plus 1. So we're taking this result that we're trying to prove and we're assuming it's true for some value of n. And we now need to prove that on the basis of this assumption, the result would also be true for the next value of n, which is k plus 1. Now, we're going to do this slightly differently to how we did the previous question. We're going to find ourselves the target expression. So if the result is true for n equals k plus 1, on the right-hand side, we would expect to get the format of this result here, but n would be replaced by k plus 1. So what would this target expression look like? So if the result is true for n equals k plus 1, then our target expression would be the right-hand side, but n would be replaced by k plus 1. So I would get k plus 1 over 6, and in the second bracket I would get k plus 1, which I'll just write like that for the minute, and then in the third bracket I'd get 2 brackets k plus 1 and then plus 1. So you can see I've taken n and I've replaced it by k plus 1. Now, what does that simplify as? Well, that would then tell me my target expression should be k plus 1 over 6, k plus 2, and then in the third bracket 2k plus 3. So if I get to this result here, I know my proof by induction has worked. Let's try it. So to find the sum of k plus 1 squares, we are adding together 1 squared, 2 squared, 3 squared, all of the square numbers up to the k squared value and then the k plus 1 squared value. Now, what do we know about the sum of the first k squared numbers? We assumed that this was given by k over 6, k plus 1, 2k plus 1. And we're now adding to that the k plus 1 squared value. So in yellow, remember, that's the assumption we made about the sum of the first k squares. And we're adding to that the k plus 1th square. So overall, that will give us the sum of the first k plus 1 squares. Now, how do I simplify this? Well, those of you tempted to do some wild expanding here, stop, hold your horses. Factorisation is crucial here. Can you see that we could take out a factor of 1/6 and a linear factor of k plus 1, a much more sophisticated approach here than some crazy expansion. So if I take out a factor of a 6th k plus 1, I'm left with, in the first part, k bracket 2k plus 1, and in the second part I'm left with 6k plus 1. And now we can do a little expanding. So in the big square brackets, what do we get? We get 2k squared plus 7k plus 6, which hopefully you can all see straight away will factorise further, the green part there. So that will factorise to give me this. Now I'm just going to reshuffle this a little bit, and can you see we have the target expression? Go back, look at the target expression. So this is the target expression. that we wanted to get to. So we've done it. Now, if you want to, you can be very sophisticated and show that in each of these brackets, k is effectively being replaced by k plus 1. So, for instance, this bracket here, you could write it as k plus 1 plus 1. So that's the equivalent of k plus 1, but the k replaced by k plus 1. And then in this bracket over here, I'll do this one in blue, you can see that this is 2 lots of k plus 1 plus 1. So you can see here we have the structure of 1/6 of n, n plus 1, 2n plus 1, but the n has been replaced by k plus 1. So all that remains is for us to write our conclusion. Please don't skip this part. It's actually really important that you conclude your proof by induction appropriately. So if the result is true for n equals k, it must also be true for n equals k plus 1. And as the result is true for n equals 1, by induction, it must be true for all n greater than or equal to 1. Absolutely crucial to follow the format of this wording I've used here. You must mention that you have done the proof by induction. You must reference the fact that the result is true for your starting case, i.e. for n equals 1, and draw these statements together to form your conclusion. Don't skip any of this out. So having proven that the sum of the square numbers is given by the formula that we've been using in the standard series results, can we now prove using induction that the sum of the cube numbers is given by this standard result here? So let's have a look at what we've got. On the left-hand side, we are clearly referring to the sum of the cube numbers, 1 cubed plus 2 cubed, plus all the way up to n cubed, and we are proving by induction that this is given by the formula that we made quite considerable use of a few lessons ago, n squared over 4, n plus 1 all squared, but we're going to prove it using induction. Now it's up to you. You may want to follow this through with the video if you feel like you need to build your confidence in this concept a little bit more before moving on your own, or you may wish to have a go yourself and then come back and look at the video and see how it compares with your work. So our first task, prove that the result is true for our starting case. Now again, our starting case is n equals 1. That isn't always going to be the way. It just has been for the examples that we've done in this lesson, and quite often n equals 1 is the starting case, but you will come across some examples where it's not. So as long as you prove that it's true for your starting case, you're absolutely fine. So for n equals 1, the left-hand side, well, that's just the sum of 1 cubed, which is 1. Now the right-hand side, that will be 1 squared over 4, 1 plus 1 all squared, and work that out, that also equals 1. So we can confirm here the result is true for n equals 1. Let's make sure we've written that down for clarity. So the result is true for n equals 1. So, next step, we need to make the assumption that the result is true for n equals k. So if the result is true for some integer n equals k, this then tells us that we're saying 1 cubed plus 2 cubed plus 3 cubed plus all the cube numbers up to and including k cubed must be given by this result here, with n, of course, replaced by k. So k squared over 4, k plus 1 all squared. So now we need to consequently prove that on the basis of this assumption, the result must be true for n equals k plus 1. Now, if the result is true for n equals k plus 1, then our target expression is going to be the right-hand side here with n replaced by k plus 1. So k plus 1 all squared over 4, and then k plus 1 all squared, which of course is the same as k plus 1 squared over 4, k plus 2 all squared. So if we get down to this result here, then we've achieved our target result. So now what do we have to do? Well, we have to find the sum of the first k plus 1 cubed numbers, so this summation here. So we are looking for 1 cubed plus 2 cubed plus 3 cubed plus k cubed plus k plus 1 all cubed. Now, we made an assumption. We assumed that the sum of the first k cubed numbers, now we assumed that this was equal to k squared over 4, k plus 1 all squared, and we're adding to that, of course, the k plus 1 cubed value to get the sum of the first k plus 1 cubes. So let's simplify this. Again, no expansion. We're going to do some very neat factorisation. Take out a quarter of k plus 1 squared. What's left when we do that? Well, k squared for this yellow part here, and for the blue part, 4k plus 1. Close our bracket, and then keep simplifying. We've got a quarter, k plus 1 squared, and then in the green bracket, k squared plus 4k plus 4. Now, this simplifies to a quarter, k plus 1 squared, k plus 2 squared, and hopefully you've spotted that this is the target expression which we were aiming for. And you can just rewrite this to show that this is k plus 1 all squared, and then here k plus 1 all squared. So effectively it's the original result that we're trying to prove, but with n replaced by k plus 1. So we've completed our proof, and we just need to write down our concluding statement. So if the result is true for n equals k, it must also be true for n equals k plus 1. And because the result is true for n equals 1, by induction, very crucial to include that, it must be true for all integers n greater than or equal to 1. Now, a nice note, you may have come across this before, if you want to show that you've completed your proof, you can write in a QED. So here's a quick summary of the key steps that we have looked at. Firstly, prove that the result you're trying to prove overall is true for a starting value. It's often n equals 1, it's not always n equals 1. Assume, or make the assumption, that the result is true for some integer k, and then write down the result as if it is true for this value. Now, you then need to prove that if the result, and it's a hinging on the if the result is true for n equals k, it must also consequently be true for n equals k plus 1. Now, it may help here to write down the target result, which I did refer to as the target expression, same concept. So the result, if it were true for n equals k plus 1, this gives you something to aim for with your algebra. Now, you must then explain that if the result is true for n equals k, it must also be true for n equals k plus 1. And because the result is true for n equals 1, by induction, it must also be true for all values of n greater than or equal to 1, i.e. the equivalent starting value if you didn't start with 1. Now, you must conclude the argument by writing down the result and stating that it has been proven, and you must refer to induction in your argument. Follow the format of the statements that I've given you in the examples that we have done. Now, having studied this really carefully, we're now going to look at 3 further examples taken from exam questions to give you an idea of some of the different questions that you might be asked about proof by induction. After this, there is a second lesson involving proof by induction, which is directly related to the concept of recurrence relations. So let's take a look at this example here. We're going to prove this result by induction. So let's start off by just trying to think about what this result actually means, this summation here on the left-hand side. So if r is equal to 1, we then get 1 multiplied by 3 to the power of 1 take away 1, which is 0. So the first term is 3 to the 0. Now it's a summation, so we're then adding on the second term. What happens if r is equal to 2? Well, then you get 2 multiplied by 3 to the power of 2 take away 1, which is 1. So that's the second term. And then the third term, if r equals 3, you get 3 multiplied by 3 to the power of 3 take away 1, which is 2, so on and so forth until you get to the nth term, which is n multiplied by 3 to the power of n take away 1. Now, these brackets are fairly meaningless, but I'll just put them in for clarity so you can see the terms separated together. So we are proving that the sum of the n terms of the sequence generated by this formula here is given by this result here. So we're proving that this has a total of 1/4 3 to the power of n 2n minus 1 plus 1. Quite complex, there's a lot in that actually. So let's start off, let's prove the result is true for n equals 1, which is our starting value. Again, you can see from here we're starting with a value of 1. Now, the left-hand side is then simply the sum of one term, and we know, we've worked it out previously, that's 3 to the power of 0, which is equal to 1. Now, the right-hand side is a little bit more complex. We need to now substitute r equals 1, n equals 1 into the right-hand side, which is 1/4, 3 to the power of 1, 2 times 1, which is 2, take away 1 plus 1, and let's work this through. So that's 1/4, 3 multiplied by 1 plus 1, which is of course going to give us 4, so this ultimately gives us an answer of 1. So make sure you state that you've proven the result is true for n equals 1. Now let's make the assumption that the result is true for n equals k. So this then tells us that the sum of the first k terms generated by this formula here is equal to 1/4 of 3 to the k, 2k minus 1 plus 1. Okay, so just in case anyone's not too sure about what this means, this here means we're adding together 3 to the 0 plus 2 times 3 to the 1 plus 3 times 3 squared plus all the way up to k multiplied by 3 to the k minus 1. So that is the sum of the first k terms, and we're assuming that it is equal to this result here. So now, on the basis of this assumption, we have to prove that the result is true for n equals k plus 1. So I think it would be useful for us to identify our target expression here, which of course is the right-hand side with n replaced by k plus 1. So that means that our target expression, if we can prove this is true for n equals k plus 1, would be 1/4, 3 to the power of k plus 1, 2 lots of k plus 1 minus 1, and then a separate plus 1, and then close off the bracket. Quite complex. Let's just simplify this down a little bit. So our target expression, 3 to the k plus 1, and then inside the bracket here we'd be expecting 2k plus 1, and then a separate plus 1 here. So this is what we're aiming for when we work out the result for n equals k plus 1. So what we now need to do is find the sum between r equals 1 and k plus 1 of r multiplied by 3 to the r minus 1. So, of course, this is then equal to as we know, the sum of the first k terms plus the k plus 1th term. So I can write down that this is equal to this plus k plus 1, 3 to the k plus 1 minus 1. So just check you understand exactly what's going on here. This part here, of course, is the sum of the first k terms. And what I'm trying to do is then add on the k plus 1th term to this. So what do we know about the sum of the k terms? Well, we made an assumption about the sum of the k terms. We assumed it was equal to a quarter, 3 to the k, 2k minus 1 plus 1, and the k plus 1th term is k plus 1, 3 to the power of k, because of course this part here simplifies down to just k. And we now need to show that this is equivalent to our target result over here. So I'm going to move on to the next slide so I have a little bit more space for my working. So here's the result that I'm working with on the left-hand side. I've got to show that this can be rewritten in the format of the target expression. So a good way is to keep working with the target expression in sight, have that in view so you can see what you are aiming for. Okay, so here we go. Now it's clear that there's a factor of 1 at the very end of this, which will be multiplied by a quarter. So what I'm going to do is say that we've got a quarter, 3 to the k, 2k minus 1 plus a quarter, so expanding the yellow part out. And then the red part I will leave as k plus 1 multiplied by 3 to the power of k. Now if you look at the target expression, there's a factor of a quarter at the end of this, which we have already in place. So here's what we're going to do. We're going to rewrite 1 quarter multiplied by 3 to the k, 2k minus 1. Next to that, I'll have the red part, k plus 1, 3 to the k, and then I'll conveniently just move this factor, this part a quarter, to the very end so we can deal with it later on. So let's look at this. We need to factorise out 3 to the power of k here, and also a factor of a quarter. So let's do that here. So let's take out a quarter and then 3 to the power of k. And then what do we have? We have 2k minus 1 plus 4k plus 1, and then plus a quarter at the end. So let's simplify what we have in large square brackets. And we have 6k plus 3 so we have a quarter, 3 to the k, and then 3 brackets 2k plus 1. Don't forget that we have this quarter, which must continue the whole way down, and then eagle-eyed amongst you will see we are pretty much there, because 3 to the k multiplied by 3 to the power of 1 can be written as 3 to the k plus 1. So we have a quarter, 3 to the k plus 1, 2k plus 1, and then plus a quarter at the end. And all that remains to do is potentially factorise out the factor of a quarter. So we then have 3 to the k plus 1, 2k plus 1, plus 1. And that is the target expression. So we have proven that the result has now got to be true for n equals k plus 1. Let's write our concluding statement. So if the result is true for n equals k, it must also be true for n equals k plus 1, and as the result is true for n equals 1 by induction, it must be true for all integers n greater than or equal to 1. So next example, we're going to prove by induction this result over here. So let's start with proving that the result is true for n equals 1. So the left-hand side is simply equal to 1 squared, or 1. Now the right-hand side of this alternate sum of squares here would be equal to negative 1 to the 1 minus 1 multiplied by 1, 1 plus 1 all over 2. So that's negative 1 to the power of 0, which is just 1, multiplied by 1 multiplied by 2 over 2, which of course is 1. There's like an awful lot of working just to show that something is equal to 1. So the result is true for n equals 1. Now, next stage, we want to assume that the result is true for n equals k. So we're going to assume the result is true for some integer n equal to k, which then tells us that 1 squared minus 2 squared plus 3 squared minus 4 squared plus all the way up to the kth term must be equal to negative 1 to the k minus 1, k multiplied by k plus 1 all over 2. Very complex, there's a lot to think about here. So this is the result for n equals k. So if the result is true for n equals k plus 1, what would the target result be? So what's the target result for n equals k plus 1? Well, we would expect to get negative 1 to the k plus 1 minus 1 multiplied by k plus 1 multiplied by k plus 1 plus 1 all over 2. So I've replaced n by k plus 1 on the right hand side. So just to simplify this a little bit, this is negative 1 to the power of k, and then k plus 1 multiplied by k plus 2 all over 2. So this is my target expression and what I'm aiming to get to when we take the sum of the first k plus 1 terms. So now we're going to prove the result for n equals k plus 1. So what would that actually look like? So that would look like this. So we would then have 1 squared minus 2 squared plus 3 squared minus 4 squared plus ... plus negative 1 to the k minus 1 k squared plus negative 1 to the k plus 1 minus 1 k plus 1 all squared. Okay, so make sure you can understand this really carefully. This is the collection of the first k terms, and this is the k plus 1th term. Okay, now the part in yellow we know we have assumed to be equal to negative 1 to the k minus 1, k bracket k plus 1 over 2, and then we're adding on this k plus 1th term, which of course is just negative 1 to the k plus 1 squared. Now here comes the factorisation, crucial to this process as you can see. So what can we take out? Well, we can take out a factor of a half, which will be useful to us. Always look at the final result and see what you're trying to get to. Now we want there to be a negative 1 to the k in that, so I'm going to take out a negative 1 to the power of k, And then I'm also going to take out a k plus 1. So far I've got this part, and this part all ready to go. So what's left when we take out those parts here? So in the big square brackets. So for the yellow part, we're going to need a -1 to the -1 to give us our k minus 1. And we're going to need a k and nothing else. And then for the orange part, we're simply going to need a 2 to cancel with the half, and a k plus 1. Check back in your head that the multiplication works when you expand. So simplifying this, we've got a half, -1 to the k plus 1, and then in the big blue square brackets, let's see what we've got. Now -1 to the power of -1 is just -1, so we've got -k plus 2k plus 2. And as you can see, we are pretty much there. Here we go. And then the part in blue simplifies down to give us k plus 2. So this is the target result. Now you see why using a target result makes life quite easy. In comparison, the alternative to that is to do what we did in the very first example, which is to prove that the result you've got is the original result with your n replaced by k plus 1, and that can be a more complex way of doing things. Don't forget to write your concluding statement. So make sure you include your concluding statement at the end. Don't forget you've got to refer to the fact that you have used induction. If you want to, remember, you can put in QED at the end to state that you have concluded your proof. And so we come to our last example of this lesson. Prove this result by induction. So it is another summation result. We are proving that the sum of 1 over 2r minus 1 to r plus 1 between r equals 1 and n is equal to n over 2n plus 1. So that's what we are proving by induction. So let's start off by looking at what happens when n equals 1. Now the left-hand side will consist of one single term, 1 over 3, and the right-hand side will be 1 over 2 times 1 plus 1, which is also equal to a third. So the result is true for n equal to 1. So now let's make our big assumption that the result is true for some integer n equals k. Now we must write out what we mean by that. So we are saying that the sum between r equals 1 and k of 1 over 2r minus 1 to r plus 1 is equal to k over 2k plus 1. So we're effectively saying that 1 over 1 times 3 plus 1 over 3 times 5 plus all the way up to and including 1 over 2k minus 1, 2k plus 1 is equal to k over 2k plus 1. So this part here is just this written out in terms. So we're going to use that assumption, and we're also going to show that based on this assumption the result must be true for n equals k plus 1. So we need to find out what is the target result for n equals k plus 1. So the target result for n equals k plus 1 is of course this result here with n replaced by k plus 1. So that would simply give us k plus 1 over 2 brackets k plus 1, which simplifies to give us k plus 1 over 2k plus 3. So this is our target result that we're aiming for. So now let's prove that the result is true for n equals k plus 1. So let's think about the left-hand side, of course, which is the sum between r equals 1 and k plus 1 of 1 over 2r minus 1 to r plus 1. Now, we know that we can split this up into the sum between r equals 1 and k, like this. But of course, we have to add on the k plus 1th term if we want to make sure we're working out the sum of k plus 1 terms. So we've got the sum of the k terms in yellow. The k plus 1th term would then be 1 over 2 bracket k plus 1 minus 1 to bracket k plus 1 plus 1. Can you see what I've done there? I've taken the formula for the nth term and I've replaced n by k plus 1, or r by k plus 1. So what do we know? Well, we made an assumption about this yellow part. We made an assumption that that was equal to k over 2k plus 1. Now this red part simplifies in the denominator to 2k plus 1 bracket 2k plus 3. So we have this now. Let's remind ourselves of what the target expression was. So our target expression, if you recall, we need to get to k plus 1 over 2k plus 3. So let's see what we can simplify here. Okay, so no factorisation yet because we have a pair of algebraic fractions. So we need to find ourselves a common denominator here. So we're going to have k bracket 2k plus 3 plus 1 all over 2k plus 1, 2k plus 3. Now let's take a look at that numerator. 2k squared plus 3k plus 1. And hopefully you can see what I'm seeing, that the numerator is going to factorise into something very helpful. So the numerator factorises as 2k plus 1, k plus 1. And then, of course, that allows us to cancel out these parts here, and we are left with k plus 1 over 2k plus 3, which is the target expression. So we have proven that the result is true for n equals k plus 1. The last thing left is to make sure we write down our concluding statements. Now, I've run out of space on my page, but I want to include it on the same slide for you. Make sure your conclusion is written neatly underneath the rest of your work. So if the result is true for n equals k, it must also be true for n equals k plus 1, and because the result is true for n equals 1 by induction, it must be true for all n greater than or equal to 1.